All right, welcome to IM2 for LP9 days 1 through 5. We are going to be working in chapter 12. I forgot to put the title in there, so I forgot to type the little title right here. So we're going to be working in chapter 12 this week. As always, I'm going to start off with the class expectations here. So make sure, definitely, I want you to understand how the grade is calculated. Homework is one of the more important pieces here because it's worth such a big chunk of your grade. It's worth 50% of your overall grade. So you definitely want to be logging into alex.com and working on the homework assignments. Not saying that you don't want to work on anything else. Of course, you want to work on the other pieces, but that's a big one. If we're not working on homework, that's definitely going to bring down our grade and we will not be passing. And when you log into alex.com and you go up to the top and click on those 3 lines, you can go to assignments or gradebook and it will actually show you which category it fits in. It'll say homework, topics, quizzes, or tests right next to it. And what we call quizzes, they're actually called reviews on there, but it does say quiz in the little category section. So we definitely want to make sure we're logging and working on these. Topics, that's, we get 10 of those a week to go through and complete. That's based on individuals, how you did on your initial knowledge check. So it's going to kind of change up based on the student to help you bring up that math knowledge, that math level, to help you with your current homework. Tests or quizzes just depends on that Monday, whether or not we finished a chapter in the previous week or we're still in the chapter. If we're still in a chapter, then we're going to be doing a quiz. If we're finished a chapter, we're going to be taking the test for it on that Monday. So kind of just depends on which one there. But make sure these are smaller pieces, but definitely make sure you're working on all of these pieces, because if we're not doing, say, the tests up to this point, and we've only taken 3 or 4 tests at this point, but that means that that's 20% of your grade kind of being held hostage. You don't even have the chance to earn those points if you're not working on those tests or those quizzes. Okay, it's just being taken away from you. So definitely make sure you're going and completing those tests and those quizzes and the weekly topics, because those are points that they don't seem as big as the homework, but they definitely add up quickly. Attendance, I know it's been a little funky this semester with attendance with some of our schedules, so especially with the last couple weeks of state testing, but we will be going back to class next week, so I can't wait to see everybody. But we definitely want to see you in class, and that's why I'm creating these videos as well to help us keep going as far as a classroom, some kind of setting there. So our completion, make sure you're logging on to alex.com. We complete all of our homework on alex.com, except for every once in a while we do classwork, although we're not doing that this week since it's off of a video. You're going to have to do all of it on alex.com. All weekly work is due on Sunday. You get an automatic 1-week extension. So if you don't have it done by that week on Sunday, you automatically have till the next Sunday to keep working on it. If you need more extensions, let me know. I can open up any assignment from the beginning of the semester to now, except for topics. That's the only one I can't reopen because Alex calculates that on a weekly basis. So it won't go back and give you extra points for it. But any of the other pieces, I can open those up and you can work on homework assignments, tests, or quizzes. You have no penalty. There's no late penalty or anything. You will just get the points, whatever it is you get on it. If you get an A on it, you have an A on that assignment. Okay, so just let me know and I can always reopen those for you. Resources, you have your teacher, that's me, your math teacher, and your independent study teacher. Reach out, ask questions. We are your first resource. Your notes pages, if you do not have the notes pages this week, definitely make sure you reach out to either me or your independent study teacher to get them, because it's so much easier to follow along if you have them. In-center tutoring, we do have a tutor in-center. If she's not available, you can always come and ask me questions. I'm usually available before or after class, or you could even, text and ask me if I have special times to meet. The FEV tutoring, it is so easy to use. It's 24 hours, 7 days a week. You log in through your clever.com account. You literally, when you log in at the very top, you can click on demand session, and within a few minutes, you can be working with a tutor. And it's literally 24 hours, 7 days a week. You can log in whenever you want. So huge resource that I think we're not utilizing enough. I made YouTube videos for all the homework. Yep, I did all that homework too. You can find those on the QR codes on your notes pages, or you can go to the Google Classroom. I have them all there. If you bookmark my YouTube page, that also is a little bit easier, so you don't have to go back and look for it again. And did you know you can ask questions directly from Alex to your teacher? So if you go on any page on alex.com, as long as you're in a homework, test, quiz, topics, like one of the homework pages or the work pages, there's a little envelope on the right side. You can click on that envelope. It'll open an email directly to me or your math teacher, and attach a page of what you're working on. You can type your message and send it off. We know exactly where to come help you. It's amazing. So very convenient way to ask us questions. All right, so let's go ahead and look at this. So we have LP9, day 2, and we're going to look at representations of three-dimensional figures. So this is on chapter 12. We're kind of going back and we're going to review a little bit here. So we're going to classify some solids. So when we're naming solids, the first part of the name is the shape of the base. So that's the bottom. Is it square? Is it rectangular? Is it triangular? You know, what's the shape of the base there? That's the first name. The second part of the name is the type of the solid. So is it a prism, like a box? Is it a pyramid where it comes up to one point? So that helps naming the shape. So we have the shape of the bottom, and then what type of solid is it? Solids dealing with circles do not have these types of names. So instead they have one single name for the entire solid, like a sphere, which is a ball, or a cylinder, like a, like a can of soda, or a cone, like, an ice cream cone. So if it has curved surfaces or circles, then we don't do this two name situation. It just has one name to it, okay? Because theoretically the base would be a circle. So we wouldn't call it a circular cone. Well, a cone has to have a circle on it, so there's no reason to say circular. So with this one, we get figure A, B, and C, and we're just going to match them up based on, what we know about naming these. So which figure shows a rectangular pyramid? So rectangle and pyramid. So I want it to come to a point so I can see, here's my pyramid. This is the only pyramid I have, and I just need to make sure that the bottom is in fact a rectangular base, and it is. That definitely looks like a rectangle. If it was a square, that would also count because a square is a rectangle. Okay, we would usually call that a square pyramid though. So we can bubble in figure C here. All right, the next part we have a cylinder. Well, I don't see any can shapes here. So, and I even put on here a can shape, that's kind of the easiest thing to picture when we're thinking of a cylinder, or a tube, something like that. So I don't see anything like that, so this would be none. And then which figure shows a rectangular prism? So I'm going to look for prism first. Here's my prism. It's a box. And then I just need to make sure that the base is in fact rectangular. And yep, that is. So we have figure A. All right. So now we're going to practice counting the cubes in a solid made of cubes. So this would be a great visual to build with blocks, sugar cubes, Legos, math manipulatives. It would be really cool to be able to do that if your center has those. I don't think we currently have math manipulatives at my center, but I could possibly bring in Legos or sugar cubes if we really want to do this. What I did was I made a video so that we could actually see this figure three-dimensional. So the figure below shows a solid made of stacks of cubes. The answer box shows the same solid viewed from above. So literally if we could look down at it, like straight down. For each stack, write the number of cubes in the stack. So let's take a look at the video here. And this is the same solid.
This is a new program called Tinkercad, in case you don't have blocks to mess with in class. So this is kind of the view that we see on the worksheet of the figure, and they want us to take a look and see how many blocks are in each kind of column here. And so it's very cool with this program. I can take this and I can kind of manipulate it and turn it around so I can actually see all the different sides of this object instead of just that one kind of sideways view that they're giving us there. So it's just a very cool way to see that. So what they want us to do is look at it like this, and looking straight down at it, I can't see how many blocks are in there. I can see they're different color blocks, but I can't really see how many are there because you lose the perspective. So getting to look at it from the sides, we get to keep that perspective view of this three-dimensional figure, and we can actually fill in those blanks there. So I hope that helps, and it's definitely a very fun program to use, and it's totally free. So Tinkercad.com, and you can you just log in with your Google email and you can play with things. There's a Minecraft option and a Lego option too. So
okay. So looking at that piece, I'm actually gonna mute it, but pause it and fast forward just a little bit here so that we can see it again. So if I'm looking at this piece, if it'll load. So while it's loading here, I can see on this view, and we can see that on the other screen too, but I like this one because it's very colorful. So I can see there's one here, two here, one here. I can't see the green one that's behind the purple, but we will assume that it's there. And if I flip this around, you can actually see that the green is in fact all the way up to the top. Oh, and it kept going there. So you can see there are 3 green, there are 3 yellow. We just don't get to see it from that point of view, right? It gets blocked by that purple and that blue. So what we want to do on this next page here is literally just fill this in. So we're going to go through and fill in all these pieces. So I already have the 2 filled in the corner here. So I have 2, and then I have 3 and 3, and 1 here, and then I have 1, 1, and 2. So we're just filling in those pieces. You know, how many, if I look at it straight up above, and that's that interesting thing too, looking at it straight down, you completely lose the perspective. So if we were to look at this one with no coloring on it at all, and look straight down at it, it would just look like a rectangle. We wouldn't really be able to tell how many were stacked in either one. You completely lose that perspective. All right, so now this one, we're going to look at the side views of a solid made of cubes. So this is kind of the same idea. We're going to draw the left and the front views of the solid. So I have another little video. You know, if you can build this in your center with cubes and actually manipulate it and look around, that's definitely very cool. But what we want to do is we wanted to be able to look at it straight from the left side here and then from the front side. So let's go ahead and click on the video here and see what I have to say. Oh, let's rewind. Sorry. I forgot to turn the sound back on.
So this is Tinkercad again. It's just a very cool way to be able to look at this 3-dimensional figure if you don't have blocks to click together in class. So this is the figure that we see on our worksheet. And what they want us to do is they want us to look at the left and the front view of it and just draw what we see when we look at it from the left and the front. So we kind of looked at this in the last video. When you look at it straight on, when you're not looking at it kind of diagonally or sideways like this, when you change the view and you look at it straight on from one perspective, you should kind of lose a little bit. I don't have them lined up perfect, but you should lose a little bit of that idea that it's even 3-dimensional. All I see are the blocks. Now, the green one and the yellow one here, we see a little strip. We really shouldn't see those. It appears that I have these a little bit low, so we can still see those. But that's the idea, is that we shouldn't really see them anymore. We just see this shape. So this is what they're calling the left view. I turned it to the left, and I'm looking at this on the left. So if I turn this back to kind of the way that we were looking at it before, the front is they're looking at this side. So if I turn it, I know that's not labeled quite the same on my little program here, but this is the view. So we're not drawing any kind of dimension in it. We're just going to draw 3 blocks going down and 3 blocks going to the right or the left here, which it kind of looks like, you know, an L shape in a way. But this is what they want us to do, is kind of take away that dimension and just say, if I'm looking at it from one side or the other, what do I see? And there we go. That's a little bit better. I just didn't have it quite flat. So I can't really see any dimension anymore. I can tell that these are different stacks because they're different colors. But if I had made them all the same color, we would completely lose that perspective. So, all right, again, I hope this program helped just to be able to picture that object and kind of turning it around. This is a completely free program called Tinkercad. If you've never played with it before, I definitely suggest you go, mess with things. You could build all kinds of stuff, as you can see off to the side here. So, all right, I'll see you in the next video. All right, so this is Tinkercad.
Okay, so now we're literally just going to draw kind of exactly what we pictured there. So when we looked at the left view, we could see the 2 here, and I could see the 3 going across, the 1 on the bottom, and the 1 on the top here. So it looked like a big rectangle with 1 on top. And that's exactly what it looked like on that other video, right? So I'm just showing you kind of pictures so you can also picture it straight from here. And then we're also going to take a look at the front view, which is just this kind of the right side there. So we have that red one. We have this blue one here. I would still be able to see that. And then we'd also be able to see these two green and that purple one on the top. So that kind of L shape that I was referring to in the video. So I like the color coding just so that you can kind of see where am I pulling these from? What would I see? But again, it would be definitely cool if you had some kind of manipulative. You could actually turn it and look at it that way. You just need to make sure you build it exactly the same. All right, so we're going to keep on moving here. Now we're going to look at some cross sections. This is if I could slice through an object. That's what a cross section is. So identifying horizontal and vertical cross sections of a solid. So in each figure below, a plane passes through a geometric solid as shown. For each figure, choose the shape of the cross section formed. So we've got kind of this big plane going through, so like a piece of paper. If we could slice through this object with this plane, what shape would it make? So if we could picture this, so if I look at a cylinder, okay, so again, if you wanted to, this is called Geogebra. I think I'm going to do this for kind of all of our solids here just so that we can look at them because this is very convenient. So we can see the plane, there's this big blue square going through, and it's actually showing us this orange cutout that's happening. So I can shift this plane up and down, and this is actually showing me a shape of what's happening. So if I go diagonally like this, it looks much more oval. So the more I tilt it, the more oval it looks, and it kind of even cuts it off if I go up to it at the top and the bottom. But if I go flat, which is what they're doing, straight across, let's see, can I get to 0? Now we have a very circular cut, and it's actually matching the top and the bottom, the bases. So that's pretty true of all of these. If you go right across from left to right, so horizontal, it's going to make a shape that matches the base. So if it's a circular base, it's going to be a circular cut. If it was a square, then it would look like a square cut. If it was a triangle, then I would have a triangular cut. So it just depends on what that base is when you're going horizontal. If I were to go straight up and down, this one's a little different because it's a cylinder, but this would actually cut out a rectangle if I go straight up and down, if I were to go vertical. Okay, and I can turn this all around. It doesn't matter where I go on here. And if you remember if we unfold a cylinder, so if we look at the net of a cylinder, it's actually a rectangle with a square on either top or bottom. And I think we are going to look at that in this section. So if you've never seen that before, I do believe I have a whole slide that's going to look at that. But that's the idea here. So this is what a cross section looks like. We're just literally chopping right through it, and what do we get? So remember, we're looking for, specifically for this one, is a cross, but they might give you a vertical one as well. All right, so let me go back to my slide here. All right, so now we've looked at it, so we know it's a circle. So let's look at a cone. So now we're going to go straight down. We're going to go vertically through a cone. So let me maximize this guy. Again, this is the Geogebra. So if I look at this and I'm going straight down, and I want to go straight through the vertex because you can see it's kind of rounding over here if I'm not on the vertex, if I'm on the side. We don't get this nice triangle shape. But if I'm right at the vertex, there's this very, very strong point because that's how a cone works. And I have this triangle going right straight through. And it doesn't matter if I spun this around, it would be a triangle all the way around. I can tilt it, but we don't really want it tilted on this one. We want it to be straight up and down, so I want it to be 0 tilt. And I can tilt the plane as well if I want, or take the tilt off. But this just shows us, as we're moving this around, what shape it would make. If we were to cut through it horizontally, this would make a circle. It would get gradually smaller as I got closer to the top here. So I got closer to that apex or that vertex, it would get much smaller. The circle is going to be much closer to the size of the base at the bottom. And as I move toward the top, they're going to get smaller and smaller, but they'll still be circular if I were to cut across from left to right, which is horizontal. Cutting straight down through the vertex, though, I get this triangle. All right, so let's go here. So we have a triangle. And the last one is this triangular prism. So I'm going to click on here, and here's a triangular prism. So let's go here. So now I have all these different pieces that I can do. This one doesn't show me the shape over here. So this is, for whatever reason, doesn't necessarily show it to me. But I can view from the section. So I can see this too. So I'm going to turn this back. So I can see that it's cutting a triangle If I go straight across, which makes sense, the bases are triangles. I'm going straight across left to right, so it should match the base. If I rotate this so that it's a vertical, now we can see that it is making a rectangle. And that matches the sides because all the sides are rectangles. Okay? And it really doesn't matter where I rotate this. It's going to be a rectangle no matter what. However I rotate this around. Okay? The height does matter because I can take it off, but it's not really showing me that as much. But we're trying to cut straight through. Okay, so if I cut vertically through a triangular prism, it's going to be rectangle cut. If I cut horizontally, it would be a triangular cut because it's a triangular prism. If it were a rectangular prism, it would be a rectangle. If it were a pentagonal prism, it would be a pentagon. It just depends on the shape of the base there. All right, so let's go back and we're going to click on rectangle because we are going straight down on this one. So it's going to make a rectangular cut. All right, so just play with those. If you have different ones when you're doing this online, you can always go to Geogebra or just look up cross section of and whatever shape it is you're being given. And then you can, if you go to Geogebra especially, those are the little fun manipulatives that I keep finding. All right, so now we're going to do surface area of a cube. So I think that was the last one for section 1. Now we're going to go to section 2. So now we're going to start to look at surface area and volume and things like that. So we're going to find the surface area of this rectangular prism. Be sure to include the correct unit in your answer. So whenever it says that, that means that we need to make sure that we put the unit into our answer. It's not just going to have it typed in there for us. And we will get that marked wrong if we either leave the unit off or don't put any unit on at all. And by unit, it means, what's the measurement? Is it centimeters? Is it inches? Is it feet? What is the measurement? So first we will draw the net for this prism so we can see the individual shapes. So what do we notice about the shapes? So if I were to unfold this box, here I have it. I have the bottom, the left, the right, the top. For whatever reason, I drew kind of this way, and then I have the back and the front. I just folded them flat. And again, Geogebra has some kind of fun things about nets too, if you wanted to go through and kind of look at how that gets unfolded. So what do we notice about all of these shapes? Well, they're all rectangles, right? It's a rectangular prism, and we have a whole bunch of different rectangles here. So to calculate the area of a rectangle, we're going to multiply length times width. Oh, I'm going through and labeling. So top, bottom, right, left, back, front. So I'm going to put a bunch of labels on this one too, so it's going to get a little messy with some labels. So here I have 8 centimeters. I can see that on the side here. So if I look at the bottom side, that would be 8. And that's going to carry through to all of these sides. So all of them are going to be the same. And then the 6 centimeters that's going up the side. So if I look at the front, I folded it down, but that would be this side here. So that would copy over to the other side of the front and also the back. The two heights would be the same. And then the 9 centimeters is going to carry over here. So I have 9 centimeters and 9 centimeters. And then I also have 9 centimeters and 9 centimeters. So for the top and the bottom, I have those 4 pieces. If you notice, a whole bunch more 6 centimeters popped up here. Because if this length is 6 centimeters, well, this side and this side would fold up together to make a corner, and I didn't do that quite perfect. There I made this a little too long on my diagram, but they would fold up together. So that means that this and this have to be 6, as long as both of these corners. So I filled this in because we're going to do length times width. So if I know what all of the lengths and the widths are, it makes it a lot easier to go through and fill this in. So since we have 6 sides, we need to complete this 6 times. So we have a front area, back area, top area, bottom area, a left area, and a right area. If we, again, think about what do we know about a prism and a box in general, the front and the back should be the same rectangle. As long as we're talking about, a very basic rectangular box, not one of those special ones that have different, funky shapes. But the front rectangle and the back rectangle should be the same. The top and the bottom should be the same. The left and the right should also be the same. So if I calculate it for one, it's going to be the same for the other. So I can calculate it once and then multiply by 2. I'm going to go ahead and calculate them separately here. So the front area, I have 9 times 6, so that gives me 54. The back area, I also have 9 times 6, so I get another 54. Again, they should match up. It's a rectangular prism, that's the idea here. So the top, if you look at the top over here, I have 9 times 8. So that's 72. And then the bottom, here in the middle, I have 9 and 8 again for my length and my width. So I have another 72. And then the left area, I have 8 and 6. So that gives me 48. And then the right, I have 8 and 6 again. So that gives me another 48. So here's my 6 different pieces. And I'm going to add them all together. So 54 plus 54 plus 72 plus 72 plus 48 plus 48. And we get 348 centimeters squared. This is not a volume. You would not cube it. So this little number tells us how many dimensions we're dealing with. If there is no number, if it was just centimeters, that's one long length. So it'd be 348 centimeters long. So one line. If I have squared, what that's telling me is how much flat space does it take up. That's why it's nice to flatten it out so that I kind of realize that I'm looking at a flat space. But it's going to have length and width to it. And if you think about each one of these, it was 9 centimeters times 6 centimeters. Well, it's centimeters times centimeters. So it's 54 centimeters squared, because I'd go centimeters times centimeters. Just like a variable, I can do the same thing with units like that. Cube has to do with a 3-dimensional box, like literally how much could I fill it up with. So that little number does matter a lot. It tells us what we're measuring. All right, let's go to problem number 2. So we're going to do surface area of a triangular prism. So the triangular prism has 5 faces. 3 of them are rectangles and the other 2 are triangles. So we're going to go ahead and we're going to draw our pieces here. So we're going to draw the 2 triangular faces. So I have my 2 triangles here on the side, and we know it's 18 by 24. I also know that this is 30, but I'm not worried about this one yet, and I'll explain in a minute because we're going to review how to find the area of a triangle. I care about this 90 and the length and the width, or the base and the height. So that's why I'm only marking 18 and 24. And then I'm going to draw the base rectangle. So the bottom, I have 29 and 18. The top triangle, that's the one on the top, like kind of the ramps here. If this was a ramp, it'd be a very steep ramp. But we'd have 29 and 30. I know it's on the other side here, but I was trying to make it a little cleaner. I switched it to the side. And then we also have the back rectangle here, which would be 29 again. Even though the 29 is not there, I can transfer it back there by 24. So here are my 5 surfaces. I need to calculate the area of all 5 surfaces. So the 2 triangular faces are right triangles with a base of 18 feet. And I know they're right triangles because they actually give me that little right angle. It's hard to see, but they give me a little 90 there. So I know that that's a right angle. So they have a length of 18 feet and a height of 24 feet. So the area of the triangle is given as follows. We have area equals 1/2 base times height. Remember, it's 1/2 because it's half of the rectangle it would have been. Usually, like for a rectangle, you do length times width. And we switch those words to base and height in a triangle. It's the same thing, though. We're literally looking for the length and the width of that 90 degrees. And we're going to cut it in half because it's half the rectangle it would have been. So we have 1/2 times 18 times 24, and we get 216. But we have 2 of them. So we're going to multiply by 2 because I have 2 triangles. So really, I could have not divided by half here, but that's part of the formula. So I went ahead and went through the math there and did that part. But we end up multiplying by 2, so it kind of undoes that dividing piece. Brings us back to 432 feet squared. All right, so now I have the area of the rectangle is length times width. So we're going to do that for all 3 of these. So the base, well, that was 29 times 18, so we get 522. The top, that's 29 and 30. So we get 870, and then the back, that's 29 and 24. So we get 696. So we have our lengths here. So the total surface area, S, usually it's capital S when we do that, is the sum of the 5 areas, or the 5 faces. So here is what we get. And I filled this in instead of, I should have put this back to just the 432 because I had us do that, but I did 216 and 216. So 216 plus 216 plus 522 plus 870 plus 696 is 2,520 feet squared. And again, do not forget to put the feet squared on there. You will get it marked wrong if you leave it off or if you use the incorrect unit. So if you just did feet, that is not correct. If you did feet cubed, that is not correct. It has to be feet squared because it's an area. So it's two-dimensional. All right, problem number 3, we're going to look at the surface area of a cylinder. So find the surface area of a cylinder with a base diameter of 8 inches and a height of 6 inches. So here is our cylinder. We're going to use 3.14 for pi, and we do not want to round our answer. Be sure to include the correct unit. So they don't want us to type pi into our calculators. They want us to type in 3.14. If you actually click the pi button on your calculator, you're going to get a very long, non-repeating, non-terminating decimal. It does not end. So they want us to round pi to simplify this problem a little bit. So the net of a cylinder is made of 2 regions. The 2 bases are circles, and the middle region is a rectangle that has been rolled up. So what does that look like? So if I draw this, if I look at this one, and I like this little link here, so I can actually open it up. So I'm gonna go full screen here. I'm gonna open this up and zoom out a little bit so you can see it. So you can see we slice down. So first I open the can, so there's my lid, and then I literally cut down. So I'm actually slicing the can open, and I'm going to unfold it. So there's my rectangle that I can see, and then if I flatten it out, boom, I have my 2 circles in my rectangle. And if you notice what they're doing with the lines around the circles, do you notice if I keep going with this, they literally roll out to be the length of the rectangle. So that's actually very important on how we're going to calculate this, because that does make a difference. So the circumference of the circle is actually the length of the rectangle. So I really like that little visual because it's super cute. You know, it just helps you see that unrolling of that cylinder, that can. All right, so we're gonna minimize that and go back to our meeting here. So let's go ahead and draw this. So here's my rectangle with my 2 circles on it because I like to do this. So remember the length of this rectangle is the circumference. It's those 2 lines that were coming off of the circle, and they literally roll out to be the length. And the width is the height of the cylinder, okay? So the area of each circle is pi r squared, and they tell us what the diameter is. The radius is 4 inches, and how do I know that? Well, the radius is half the diameter. If I know the diameter is 8, I'm going to take half of that for the radius. One side length of the rectangle is the height of the cylinder, so we already know that. I think, where is it? Oh, that should have been filled in with 6 inches. I totally forgot to fill that in. So that should say 6 inches there because we know the height of the cylinder is 6 inches. The other side length is the circumference of the circle, and the formula for circumference is 2 times pi times r, or diameter times pi, because 2 times r is the diameter. Okay, either way, if you remember that one. So the area of the rectangle is length times width. Well, length is 2 times pi times r, so 2 times pi times 4, and the width is 6. So we're going to go through and we're going to start to fill this in. So circle number 1, we have pi times 4. That's pi r squared, pi times 4 squared. So I'm filling that in for the pi r squared. The second circle is the exact same because the top and the bottom circle are going to be exactly the same area. So I could also just say times 2. And the rectangle is going to be 2 times pi times r times the height. So here we have the whole formula. So now we're going to start working this out. So 4 squared is 16. 4 squared again is 16. 4 times 6 is 24 times 2 is 48. So now I'm going to combine these. 16 plus 16 plus 48 is 80. And this, I haven't done the 3.14 yet. I kind of leave that for the end. So now we're going to go 80 times 3.14, and that gets us our final answer here of 251 and 2/10 inches squared, or 0.2 inches squared. So this just gets us there. So this one's a little different because you have to realize that length is the circumference because they don't tell you that, right? You have to know, number 1, how to unroll the can for the shapes that you're looking for. And then also, how do I calculate the length there? Since you rolled it around that circle, when you unroll it, it'll be the same circumference, the same length. All right. So we are moving. Not quite sure why. We skipped section 3 here. Interesting. So we skipped over from day 3 to day 4. I'm going to section 4, which is the volume of prisms and cylinders. So the volume of a rectangular prism. So now we're going to look at the volume. I think volume is a little easier. It's kind of a little more straightforward. Then the surface area is a little bit more involved to calculate there. So the volume of a rectangular prism with length L and width W and height H is computed as follows. We have volume equals L times W times H. We literally just multiply length times width times height. You do need to make sure if they give you extra information that you identify which is my length, which is my width, and which is my height. Sometimes Alex likes to give us extra information to see if we know what to do with it. Do we actually know what we're supposed to be calculating, or are we just grabbing numbers? So pay attention to that piece there. So the length on this one is 9, the width is also 9, and the height is also 9. So this is actually a cube, not just a rectangular prism, but it's a special rectangular prism called a cube because all the sides are squares. So this means I'm going to go 9 times 9 times 9. I could also say 9 cubed. See how fun that is? It's named right after the shape. So 9 times 9 times 9, or 9 cubed, is 729. And this is feet cubed. Now I'm talking about volume. I need to make sure I cube it. Each one of these had a feet. So feet times feet times feet. If I were thinking about, a variable, I would have 3 of those being multiplied. So that's a cube. Same thing with the unit. Feet times feet times feet is feet cubed. All right. So 3-dimensional measurement. All right. So now we're going to look at a word problem involving the volume of a rectangular prism. A concrete foundation for the building has the shape of a rectangular prism. And I say draw it. So I'm drawing it down here. The foundation is 14 yards long. So here's 14 yards. 12 yards wide and 2 yards high. If concrete costs $4 per cubic yard, how much did the concrete cost for the foundation? So you don't have to draw a super fancy one, but at least draw something so that you know what you're picturing. What am I actually calculating here? So what are you being asked to find? We're being asked to find the cost of the concrete used for the foundation. Okay, so that's actually the question it's asking, right? How much did the concrete cost for the foundation? What do you need to know to answer this question? Well, if I know that it costs $4 per cubic yard, I need to know how many cubic yards I used, right, to make this concrete. So I'm going to need to know the volume. That tells me how many cubic yards I used. How much concrete is being used is the volume. Then we can use that to find the total cost. So I can multiply that by the cost per cubic yard. So let's find the volume. Length times width times height, so 14 times 12 times 2. And that gets me 336 yards cubed. So we used 336 cubic yards. Each one of those cubic yards cost us $4. So we're going to multiply this by 4. That will tell me how much it costs. They don't want to know what the volume is. They want to know the cost. So I'm going to multiply by $4, and that's going to tell me that I spent $1,344 for the total cost of the foundation, because each one of these cubic yards cost me $4. Okay, so this one's a little bit farther. We learned how to do the volume of a rectangular prism, then we applied it to a more real-world situation. Why would I use volume in real life? All right, so now we're going to look at the volume of a triangular prism. Every triangular prism has 2 faces that are parallel and congruent. So that's actually every prism. That's not just every triangular prism. They're going to have 2 faces, and it just depends on the shape on these ones. So these faces are called the bases of the prism. In a triangular prism, the bases are triangles. Hopefully that makes sense. Triangular prism, triangular bases. The distance between the bases is the height. Even though it's laying down, we still call that the height. Okay, so I have a triangle base, and then the distance between those is called the height. So we want to make sure we're paying attention to that. The 2 bases are going to be parallel to each other, and they'll be the same shape. So I know I have a lot of rectangles, but none of the rectangles on the sides here are parallel to each other. The only 2 that are parallel to each other are the triangle in the front here and the triangle in the back. So the volume of any prism can be found as follows. We have base times height, and this is a big B. Well, what does big B mean? Big B, it refers to the area of the base. So whatever shape that base is, we need to know how to calculate the area for it, because that's what the big B stands for. And this is any prism, we really like to use this over and over again because it's a very common or a very easy way to remember. We're going to do the base area times the height. We just need to know how to find the areas. So the area of a triangle is 1/2 little b for the base times the height. So big B means the base, the area of the base. Little b has to do with the length. Okay. And yes, they do use both of these so that you have to kind of know the difference between the two. And then we have two heights. We have a height of just the triangle, and we have the height of the entire prism. So when I put this all together, we have 1/2 base times height. That's our triangle. And then we also have to multiply that by the height of the entire prism. So yes, there are two h's. They refer to different things. As far as I've seen, we do not refer to them differently as far as like one capital, one lowercase. They're just both heights. So the base length of the triangle face is, is 8. So I have 8 along the bottom here. And the height of the triangle is this dotted line that's perpendicular. We always want to find something, a perpendicular length from the vertex to the base, okay? So we're looking for that square that tells us it's a right angle. So we have a height of 8 and a base of 8. And the height of the whole prism is this side between the two triangle bases, which is 10. So now let's fill this in. So we have 1/2 base times height times height. So now if we multiply all this together, we get 320 degrees centimeters cubed. Don't forget the cube. Okay. So now we're gonna, I thought there was an application problem. I guess we skipped the application problem for the triangular prism. I think we do one for the volume of a cylinder, so we'll look at that when we get there in a minute. So the radius of a cylindrical construction pipe is 2 feet. If the pipe is 18 feet long, what is the volume? Use the value 3.14 for pi and round your answer to the nearest whole number. Be sure to include the correct unit in your answer. So here is our construction pipe, and we know the radius, we know the height. The bases in this case are the circles, right? Those are our parallel bases. And even though this isn't a prism, that's still true of a cylinder. We're just dealing with circles instead of anything with a vertex on it. So the pipe is a cylinder. We can find the volume of a cylinder with radius r and height h using this formula, which is base times height. Oh my goodness, we're repeating it. Again, the big B, the capital B, stands for the area of the base. And the base in this case is a circle. So we need to know, how do you calculate the area of a circle? The area of the base is pi r squared, because that's how we calculate the area of a circle. So the volume, I'm going to replace the capital B with pi r squared, and then we're going to multiply that by the height. So here, the radius of the pipe is 2 feet. The height of the tank is 18 feet. And pi, they're telling us to use 3.14. And remember, that's rounded. Do not type pi into your calculator, because otherwise you'll get an answer that is rounded, and they do not want us to round. So let's go ahead and plug it in. So instead of pi, we have 3.14. Instead of r, we have 2. And instead of h, we have 18. All right. So now we're going to multiply everything together. Make sure that you square the 2 before you multiply it by 18 or 3.14, or otherwise you'll get kind of the wrong calculation there, because it'll square the wrong piece. So make sure either do 2 times 2 or 2 squared in your calculator, and then start multiplying it by every other piece. So you get 226.08 or 800ths feet cubed. So that's the volume of this cylinder. All right, and question number 5. So we do have an application problem here. So we're going to apply calculating the volume to something a little bit more real world. So a concrete pillar has the shape of a cylinder. It has a radius of 2 meters and a height of 18 meters. So similar to what we just did, a little smaller, but similar. They were using feet, and we're going to use meters on this one. And if the concrete costs $113 per cubic meter, how much did the concrete cost for the pillar? Use 3.14 for pi and do not round your answer. So first, what is the formula for the volume of a cylinder? Remember, we're just pulling this back from the other sheet we just did. So it's pi r squared times height, the base area times the height of the cylinder. What is the radius of this cylinder? Well, they told us it was 2 meters, so we're going to write 2 meters on here. What is the height of this cylinder? Again, they told us that it's 8 meters. And what value are we being asked to use for pi? 3.14. Okay, so what are we being asked to find, and why do we need to use volume? So we're being asked very specifically to find the cost of the concrete pillar, right? We're being asked to find that. Well, in order to know, if I know it cost me $113 per cubic meter, I need to know how many cubic meters I've used. So I know how much I've spent, because every cubic meter I use costs me $113. So that we find that by finding the volume, that will tell me how much I've used, and then we can apply that to the cost. Well, we'll multiply it just like we did on that other application problem. All right, so let's find the volume here. We have 3.14 times 2 squared times 8. So pi r squared times height. So if I multiply all these together, I get 100.48 meters cubed. Okay, so this is my volume. This is not my answer. I need a cost, so I need dollars. Each one of these cubic meters cost me $113. So we're going to multiply by 113 because that'll tell me how much I spent. So for this pillar, we spent $11,354.24. Whew, that's an expensive concrete pillar. Although if you think about the size, this is a pretty big darn pillar. 2 meters, that's 6 feet tall, or 6 feet for the radius, so actually 12 feet across if we go all the way for the diameter. And the height of 8 meters, well, times 3, that's 24 feet high. So this is a huge concrete pillar. This is not a little guy. So that's definitely a lot of concrete being used. All right, so that is the end of the sections for this week. I do believe we also go over section 3, but I think it was a little repetitive for one of the sections, so I just didn't put it into the PowerPoint here. If you have any questions, please reach out to me, your independent study teacher. If you don't have your notes pages, definitely reach out because that will be more helpful to have the notes pages filled out as you go through and do your homework. I hope this helped, and I will see you in class next week.